good, and you, sir?
I'm good. Thank you very much for joining. How was your day?
It was hectic. Just doing chemistry all day, nothing much.
Serious?
Yeah, I was doing because there were some things that I was still struggling on organic, and I also went through chemical equilibrium. So yeah.
That's nice. That's nice. That's nice. So today I want us to continue with what we did yesterday. So from what we did yesterday, are you happy with everything? Eh?
Yes, I'm happy so far.
Okay, it's fine. So we'll just start by interpreting the graphs. Maybe today we can interpret the graphs, because remember, in an exam they might want you to interpret the graphs. Okay.
Okay, sir.
Okay. Okay. Today now we only have for an hour, ne?
Okay.
So let's see what we can do with this hour, ne? So now, graphs of most of the time you're going to work on graphs of concentration and rate. Okay.
Okay, sir.
Right. So graphs of concentration and rate. Okay, I just want to okay. Graphs of concentration and rate. Okay, so now I need you to, let's say that we're gonna use what we had yesterday. Remember, we had a chemical equation that was 3H2, which was in gas state, and this reacted with nitrogen, which was also in gas state. Then we said that this is a reversible reaction. Do you still remember that?
Yes, sir.
And they form ammonia. 2 moles of what? 2 moles of ammonia. NH3,
Yeah.
which is in gaseous state. So if you still remember yesterday, we were given delta H to be what? To be less than 0. You still remember, right?
Yes, sir.
Right. So now I want us to talk about when the temperature, let's say we increase the temperature, because I need you to understand what's going on when the temperature is increased.
Okay.
Bon, we're going to have so much fun on this one. I'm not going to move fast. I'll try to move slow, because by the end of this lesson, you need to understand everything that we do.
Okay, sir.
Right.
Appreciate
So we're going to use, you see this reaction that I just wrote it down now?
it.
We're going to use this reaction to explain the change to a graph of concentration and rate when the changes are made to equilibrium. So let's say we have increase in temperature.
Okay, so if you increase the temperature, okay.
Yes, increase in temperature. Let's call this temperature. What happened if we increase temperature? Let me quickly give you the graph, then we'll go through that graph together, okay?
Okay.
Right. So let's say I have a graph that looks like this. Okay, so on this graph, remember we always say the product starts from 0, right? Then when they start from 0, then they reach equilibrium. Then let's say something here happens, and then we'll talk about that. So this will be my NH3, okay?
Okay.
Right. So now we're going to say this is the concentration, okay?
Okay.
The concentration, and this will be my time in second. Okay, so now let's say that from this point here, from this point, the nitrogen will drop. How can I do this? We need to make the graph like more clear. Let's say they start dropping from this point. They drop, then when it reach this point, it start moving in that direction. Then when it comes this point, it will switch and move in that direction. Don't worry, everything will make sense now. This is N2, the nitrogen. Then let's say, because remember, hydrogen is the one that has 3 moles of H2. So this will start somewhere here. It's gonna drop, and then when it reach equilibrium, the rate will be the same. Then from here it's gonna go up again. So let's say this one is for what? This one is for H2. This is what I need us to work on today, okay?
Okay.
Right. So this one, we're going to include another graph here that I need us to go through. This one is the concentration versus time. I also need you to understand what? I also need you to understand the rate versus time. So let's quickly write the graph of the rate versus time. Then we'll go through these two graphs. Né?
Okay.
Okay. So this one, I'm going to say this is my rate here. And this will be my time in second. Right. Let's move this down. So now, the reverse reaction, remember, is the where we convert product to what? To reactant. So this is the one that will start from 0. So this will be my reverse. Let's just put it like this. So let's say this will be my reverse. Is the one that starts from 0. Then it reaches equilibrium. Then somewhere here, let's say, there will be a change. Like
Sorry,
this.
sir. Can you hear me? Because I can't hear you right now.
You can't hear me?
I can see you trying to speak, but I can't hear you.
Okay. Can you hear me now?
No, I can't.
How? Emily, what's wrong?
Wait, sir, I don't know what's happening because my speaker is up. I can't hear you, sir. I really can't hear you.
What about now?
No.
You can't hear
I can
me?
see you trying to speak, but I can't hear you. Wait, sir, let me drop real quick and then I'll come back.
Okay. Can you hear me now?
Yes, I can hear you now.
What happened?
I don't
What
know.
did you press? Or press it in?
I didn't press. I was
Maybe you
typing.
pressed something.
Or maybe it was a mistake, yeah.
I'm not sure if you'll understand this graph, but let's try. Né? Let's try to work on this. Let's go back to that one. So let's start with this one. So we are increasing a temperature. Let's start with the concentration. This is going to be the concentration graph. Né?
Okay.
Right. So the concentration graph. It's very important that you understand everything that we're going to discuss here. Please, if there's something that you don't understand, please tell me to stop so that I can explain that again, okay?
Okay, sir.
Right. So you see this time here, né? You see this point here. This point here, let's call that point T1. And then you see this is where there's another change here. Let's call that point T2. Okay?
Okay.
Right. So now, from this, let's look at what is going on at T1. Né? Can you see that at T1, from this point, from that point, our can you see that the system reaches equilibrium? Can you see that?
Yes.
So we are saying that at T1, the system, it reaches equilibrium. Tell me, how do we see that the system reaches equilibrium?
Because they are all moving at the same rate.
Exactly, they're all moving at the same rate. That's how we see that the system reaches equilibrium. So now, what is going on at T2? Look at T2. Look at this T2. What is going on at T2?
Basically, equilibrium stops. It stops moving at equilibrium.
Then, what is going on? The temperature is increased at T2. Can you see that? Can you see that?
Yes.
So, at T2, the T for temperature is increased. Are you happy with that?
Yes, I am.
Okay, so now at T2 we increased the temperature, right? So now we need to know which reaction will the system favor. I think if you still remember what we did yesterday. Do you still remember when we say, let's go back. I think I still have yesterday's notes, unfortunately. Nothing.
Like the forward.
Yes, no, I need you to remember if the temperature is increased, which reaction is favored, forward or the reverse reaction?
Okay, wait. Seeing that this is exothermic.
Okay.
So temperature is increased, right?
Yes.
Temperature is increased. We say that is endothermic. So basically, the reverse reaction is favored.
So are you saying this one we're going to favor the reverse reaction?
Because we know that. Okay, wait. Let me say it to my understanding.
Yeah, please just.
We say delta H is less than 0, right?
Yes.
And delta H being less than 0, that is exothermic.
Yes.
Yes. And then we will know that the forward reaction is going to be exothermic.
Yes, the forward is exothermic.
Yes, and then the reverse reaction will be endothermic. And then in our note yesterday, we said that if temperature is increased, then we know that it's endothermic.
Okay.
I'm looking in our notes. So me looking in our notes, I'm seeing that if it's endothermic, our endothermic is our reverse. Oh yeah, and then we said if temperature is decreased, it's exothermic.
Okay, I think you know. We said if the temperature is increased,
Mm-hmm.
the endothermic reaction is favored. Why is the endothermic reaction favored? Because we need to cool the system down. And if the temperature is decreased, the exothermic reaction is favored. Why? Because we need to heat the system up.
Yes.
So now we can see that on this given equation, going that side, this is forward, and forward favors what? Exothermic. Okay?
Mm.
And then this going that side, this is the reverse, and the reverse favors what? Endothermic. Are you happy with that?
Yes, I'm happy with that.
Okay, now listen. Okay. We are increasing temperature. So if we increase temperature, what happens is that the system, we said an increase in temperature favors what?
Increase in temperature and favors endothermic. You're trying to cool
exactly, down. Endothermic. Then which reaction is favored?
The reverse reaction.
Exactly. So you see that you got it right at first, no?
Yes!
That's nice. So you got it right. So now we're going to say that the system, therefore, we conclude and say the system, the system will favor. Okay, again we said that T is increased. The system will favor what?
Yeah. The reverse reaction.
Exactly, will favor the reverse reaction. The reverse reaction. Right. So the reverse reaction, why? To reduce the temperature. You understand? So now,
Yes, sir.
now you're going to, we need to analyze the concentration of what? The concentration of the reactants and the product. Tell me, what is going on the concentration of the reactants?
Isn't it?
Look at the graph. Look at the graph.
No.
What is going on the concentration of the H2 and N2?
H2 and N2.
Yes.
Oh, they're moving at the same, but then
No.
H is a little.
Look at, remember we need to focus and try to explain what is going on from this point. What is going on from this point? What is going on from that point? I'm sorry, that was not the right one. Remember the reactants, it's H2 and what? And N2. Look at this. Look at the graph. What happened after the temperature was increased at T2?
Oh, so we basically increase temperature, right?
Yes.
To cool down the system.
Yes. Look, remember this is the concentration, né? This is the concentration. Look at H2 and A2. What happened? Did H2 and N2 decrease or increase?
They increased.
Exactly. So the concentration of H2 and N2 increased, okay? Will increase. I hope you understand what is going on here. So now we are saying that these two, their concentration will do what? Their concentration will increase.
Yes, I understand that.
So, and then look at what is going on at the product, the concentration of the product. What happened to the concentration of the product? You see, they start from here, then they drop. So they decrease. The concentration of the product decreased. Do you understand that part? Are you happy with that?
Oh, yes, it's what we were talking about.
Yes. You see, so in an exam, this is how they might ask the question. They'll say that they'll ask you if the temperature, okay, maybe they'll need you to tell them if the temperature was increased or decreased. You know what you need to do? You look at the graph. Let's say this statement was not given. On the statement, we were not told that they did not tell us the temperature increased, and they want you to figure this on your own to see if the temperature increased or decreased. This is what you do. Listen, are you listening?
I'm listening, sir.
Okay, you know what I'm going to do? Look at this. First thing first, I'll look at the graph and I'll say, oh, looking at the graph at T2, what is this? At T2, my reactants increased. Which reaction is going to increase the reactants? Is the reverse reaction. You understand? So this tells me that endothermic is favored, and if endothermic is favored, the temperature is increased. Now you understand how to answer this in an exam.
Yes, sir.
Nice. They will say at T2, maybe they might say explain the change in T2 if the temperature increased or decreased. Then you'll say, you check, oh, at T2, my H2 and A2 increased. Which reaction will increase the reactant is the reverse. And the reverse favors what? Endothermic. Endothermic, this tells us that the temperature was increased. Okay, so now let's move to the graph. Let's analyze this graph because they might bring it in concentration versus time, or they might bring it in rate versus time. You need to be able to differentiate the two. Yeah?
Okay, sir.
So now, the most important thing is for you to know that the one that starts at 0, is your reverse reaction. That's the most important thing, reverse reaction. And then the one that starts there and on top, we start with the reactants, then we use up the reactant. This one is going to be what? This one is going to be your forward reaction. Forward reaction. Okay, so now when you have it like this, we're just gonna call this guy here our T1, and let's call where we have a change, which is this part, let's call that T2. So now what I need you to note is that, can you see that this is still my reverse reaction? This is still my reverse reaction, and then this will be my forward. So now listen, look at this. Can you see that both rates, the reverse and the forward, both of them at T2 increase? Can you see that?
Yes, I can see.
Okay, so let's take this step by step. So here we're going to analyze the rate graph. Right. So when we look at this graph, we can see that at T1, the rate of the forward and the reverse reaction are equal, and the system reaches what? The system reaches equilibrium for the first time. Can you see that?
Yeah.
The rate of the forward and the reverse are equal, and the system reach equilibrium for the first time. When we say for the first time, this tells you that this point somewhere the system will reach equilibrium again.
Yes, I get it.
Yeah, nice. So now at T2, the temperature at T2, at that T2, the temperature is increased. Right. The temperature is increased. How do we see that the temperature is increased? Remember, we look at the reactants.
Yeah, but so didn't give me a reactant.
Yeah.
Or are we using that same? Are we using that same thing?
Boom.
Are we using that ammonia?
Yes, the same.
Okay, so how do we know? So if this is our reverse reaction and this is our forward reaction, isn't it because the rate increases?
Yes. So what we need to do is to say that temperature, remember we use T for temperature, so we need to say the temperature is increased, and since the temperature is increased, this increase what? This will cause an increase in, this will increase the rate of what? The rate of both, this increase the rate of both forward and reverse reaction. Why? Because look at this graph. Both of them moved up. You see? They both moved and start from up. You understand? Okay. So now the reverse reaction is favored. The reverse reaction is favored, and then since the reverse reaction is favored, it experiences a greater increase in rate than the forward reaction. You understand that part, what I'm trying to say?
So say the reverse reaction is favored.
Yes.
Therefore it has a higher increase.
Yes. Look at this graph. The reverse reaction was below what? The reverse reaction was below that forward reaction. Can you see? But immediately we increase the temperature, the reverse reaction jumps above the forward reaction. So this tells you that it's favored. So the one that if the graph, if this one, okay, so if, how can I explain this and say the reverse reaction is favored? Both. The reverse reaction is favored. Why? Because look at now, we are using the products to create what? To create more reactants. Can you see that the reactants, they are no longer decreasing, they are increasing. Can you see that?
Yes.
Nice. I thought
I get it.
it's going to be you're going to give me problems when I explain this concept, but now you get it. Now, look at this. Let's try this again. The reverse reaction was below again. And look at this. The reverse reaction, we were creating more products at first, right? We were creating more products, then at this point, we increased temperature. Again?
Yes.
We increased temperature. They immediately increase. When we increase temperature, what happened? The rate of reaction favors both. Increasing temperature, both.
Increase the rate.
This increased the rate of both of them. But now, the reverse is the one that jumps above to the forward reaction and it starts on this point. So this tells you that the reverse is favored. Why? Because now we are using the products to create more reactants. The products are the ones that are decreasing. Look at this arrow. If the arrow is pointing in that side, it tells you that this reduces so that we can create more of the reactants.
While the reactants are increasing, the products are decreasing.
Exactly. So this tells you that at this point here, this is where we see that the reverse
Reaction is favored.
The reverse is favored.
Yes.
Right. Are you happy about that?
Yes.
So, look at this. The equilibrium is then re-established and the rate of the forward and the reverse reaction are equal again at this point. The equilibrium is then re-established again. You understand? So at this one, maybe they'll give you T3 and they'll ask you what is going on at T3. You're going to say the equilibrium is re-established and the rate of the forward and the reverse reaction are equal again.
Yeah.
Yeah.
So easy.
Wow. You know what is one thing about this graph? Look at this information. It's only for when the temperature is increased. That's why most of the learners, they find it more difficult to work with chemical equilibrium. This graph, whatever that we discussed, it's only for when the temperature is increased. So what will happen if the temperature is decreased? You see that we still have to go through all this. We still have to go through the graph of when the pressure is increased, when the pressure is decreased, when the concentration is increased, and so on. There's too
the
much.
opposite of this.
Yeah?
It would be almost like the opposite of what we are saying here.
And then if you understand that part, Pella, you know what you are saying.
What am I saying?
Say, don't do the temperature when the temperature is decreased, because I understand this. There's no need for you, sir, to explain when the temperature is decreased, because I know it will be the opposite.
The thing is, I want you to challenge me. You must send me, you see, since we did increase, you must just send me an activity on decrease and see how much of this did I understand so that I can apply. Yeah, well,
I know. I understand you. I get you now. But there's no need for us to let's take this step by step. Now let's work with when the temperature is decreased.
Okay.
Yeah. There's no need for us to move fast. Even if today we only talk about temperature, remember we have 2 hours tomorrow morning. I'm available, Kausani. Please. The issue is this thing of waking up, man. I work until late.
Okay, so it's fine. I understand.
Yes. Okay, so now we're going to work on decreasing temperature and we're going to use the same chemical equilibrium. So I just wish when you get inside an exam, they give you the same one like this one, so that everything can you can just remember everything that we are currently doing.
Also, I will smile alone in the exam.
Even if they give you the different one, just know that just apply what we did, né?
Yes, sir.
And one thing about learning, we're going to go through lots and lots of graphs, né? And then when you get in an exam, you don't even find one. Yes.
Yeah. That is so true. Yeah, but you know what? I'm so happy that I understand these graphs first because I've never understood them.
Serious?
No. There was
This tells you
time
that I'm the best.
Wow.
But there's something I need us to let's go back. There's something I need to remind you, ne?
Yes, sir.
You see on this graph, ne? Please, make sure that you understand this, ne? You see on the rate, for the rate, ne? This is very important. On the rate graph, whichever reaction is favored, whichever reaction is favored will always be on top. Whichever reaction that is favored will always be on top, ne?
Okay.
I'll kill you if you forget this one. Okay, let's say that this graph, let's start with the concentration, ne? Let's start with the concentration. So this will be my concentration. Okay, so this will be my concentration, and this here will be my time in seconds, ne?
Yes, sir.
Okay, so now when it's like this, remember the products, they always start from 0, they go up, they reach equilibrium, then let's say somewhere here something will happen, then this graph start to increase again, and we say these are my product, which will be NH3. Okay, so from that, let's say that I have the reactants. Let's say this one, let's start with this one here. This one, we know that it will go and down here, then it will start moving in that direction. Then when it reaches this point, it will decrease. Don't worry, we'll go through these things now. So this will be my H2. Okay? This will be my H2. Then I'm going to have my N2 on top. So the N2 is the one that will start here. Then it reaches equilibrium. After it reaches equilibrium, at the very same of this point, then it decreases again. And this is my N2. So let's go through these graphs. Let's go through them step by step. Ne?
Okay.
Okay. So the first one, we're saying that this is T1. This will be my T1. Okay. And if that's my T1, at this point here, let's call this T2. Okay. Right.
Okay.
So now let's talk about this one. So this one, we are saying that at T1, can you see that at T1 the system reaches what? Equilibrium. So at T1 the system, it reaches equilibrium. Okay. Then the concentration, why is it at equilibrium? Because the concentration of the product and the reactants are constant. Please listen. We are saying that the concentration of, can you see that this part here, the concentration here, the concentration are constant. Constant does not mean equal. We are not saying that they are equal. Most of the time, learners say that at equilibrium, the concentration of products and reactants are equal. No, that's not true. They are constant.
Okay.
Constant does not mean equal. So now we need to understand which reaction will be favored. Do you want me to give you a chance to tell me which reaction will be favored? Remember, this is your forward reaction and this will be, oh, I'm sorry, not the forward, the reverse, because this is the product. The reverse always start at 0. So this will be your reverse, and this will be your forward. These two are your forward reaction. So now tell me, which reaction is favored? According to your own understanding, which reaction is favored?
So, you see, let me do my math, and then I'll come back to you with a beautiful explanation.
Okay, no problem. Remember, forward, it's the forward reaction delta H, it's less than 0. The forward will be, the forward, it's exothermic.
Yes, and the
reverse will be endothermic.
Yes. So I was asking me, what was the question? Which one is the forward reaction?
No, which one will be favored between the forward and the reverse reaction? Which one will be favored?
Will we favor between the forward and the reverse? Between this. Okay, so you must
remember the temperature is this. We are decreasing temperature, ne?
It's my forward reaction will be favored because of my reactants are decreasing while my products are increasing. So I'm making more NH3s and losing N2 and H2.
Can we go to sleep now? My bed is ready for me, because now that you understand the concept, I think we can just call it a night. We can just go to sleep. So that's very correct. You know? The forward reaction is favored. Why? Let's just do this, because even if you know the best thing to do, even if you understand something, you still have to do it 100 times. Let's go back to this now. We said that an increase in temperature favors what? Endothermic. A decrease in temperature will favor exothermic. Yeah. So now we're going to say the temperature is decreased. We are decreasing what? The temperature. So this will favor exothermic. So since this favors exothermic, we can see that the exothermic is forward reaction. So the forward reaction is favored. So on this one, therefore, the forward reaction is favored. Right. So since the forward reaction is favored, the concentration of the product will increase.
Yes.
So therefore, the N. Okay, I think you know that concentration in chemistry, we write it with this bracket. If I put this bracket and say NH3, we are talking about concentration. Do you know that?
No, I didn't know.
Remember when you calculate Kc, you use the concentration of the product divided by the you don't remember that you use something like that?
I remember, sir, but I didn't know we are saying concentration dirty brackets.
Yeah, those even in acid and base, those brackets, we say this is concentration. So I'm going to say the concentration of the product do what? Increase, because you just have to tell them what you see on the graph. Look at this. These are my product. The concentration increase. So the concentration increase.
Yes.
Right. So if the concentration of the product increase, the concentration of the reactant, so the concentration of H2 and the concentration of N2, they do what? They decrease.
Please.
Right. I think you get that one, eh?
100%.
100%. So now this is the concentration versus time. But what about the rate? The rate versus time, you see? Too much work, my friend. Too much work. But tomorrow we're going to finish the graph. Then we start with the equilibrium constant, how to calculate Kc. I'm very excited that we're going to do how to calculate a Kc now. So now, let's say, let's do the rate graph now. So for the rate, this is how the graph will look like. This is time in seconds. Listen, there's nothing you can do without this information. You see, if you forget this information here, that an increase in temperature favors endothermic, decrease in temperature favors exothermic. There's nothing you can do without that. So please make sure that you keep that information in mind. Yeah? So the rate graph starts like this, and then we are saying that the forward reaction is the one that starts. We are using the reactants to form what? To form the products. So when we get at this point, the temperature decrease means that the forward reaction is favored. So now more reactants, you're going to use more reactants to form more products. So now I want you to see the difference between these two graphs. You're gonna see what is going on. Then this one reaches equilibrium. Then once it reaches equilibrium, it gets to this point. This is the reverse. Then it's going to drop. Okay? It's going to drop. Then when it drops from this point, it will start increasing again.
Okay.
Right. So we know that this one, this will be my forward reaction. Yes. And this will be my reverse reaction. Okay, so now if we look at this, now let's go through this graph. Let's go through this graph. We can see that at this point here, we can call that T1, and this point here, let's call this point there T2. So now, from this graph, look at this. We can see that at this point, both rates initially decrease, and then since both rates initially decrease, we know that, look at this, the forward reaction is the one that is decreasing in what? In the forward is the one that is decreasing, né?
Yes.
So since the forward is the one that is decreasing, this tells us that forward is favored. I'm going to explain this. Right, let's take this step by step now. So at T1, the rate of the forward and the reverse reaction are equal, and the system reaches equilibrium, right?
Yes.
At T2, the temperature is increased. This one decreased, né? So the temperature at T2, the temperature is decreased. I'm not sure. Are you taking this down, or you want me to send you this note?
You can always send the note, sir, but I'm writing.
Okay. So a decrease in temperature will decrease the rate of both of the forward and the reverse reaction. We can see that from the graph. So the forward reaction is favored, and it explains a smaller decrease in rate than the reverse reaction. So the one that is favored is going to, look at this. Look at this. The forward, the reverse is the one that drops down. You see?
Yes.
Okay. Yeah. So, and then the equilibrium is then re-established.
Yeah.
Yo, I can't believe we still have to do pressure, and we still have to do the concentration. I'm not sure if we can do pressure in 15 minutes. Not sure.
I don't know. You tell me.
Can we do pressure in 15 minutes?
I don't know, sir. Because I understand the temperature, so I don't know how the pressure looks like. So you will tell me.
Okay, it's fine. Let's do it. Let's see now.
Okay.
Let's start with increasing pressure.
Okay.
Because if we can do the pressure in 15 minutes, this tells us that in the morning we'll only do concentration, but I think we can only do increase in pressure, then morning we'll do decrease in pressure. You know why I'm available this morning? We're going to do 2 hours tomorrow, ne?
Yes.
Tomorrow is Tuesday, we do 2 hours. Then Wednesday, 2 hours. Thursday, 2 hours, ne? Then on the afternoons, we'll be doing 1 hour, 1 hour, because I won't be available from Thursday afternoon when I come back to work. From Thursday, Friday, Saturday, Sunday, Monday, I'm not teaching. That's a long weekend. That's one Talogan. Yeah, I have to travel, and then yeah, so I won't be teaching that time. But in fact, I'm not gonna even open my laptop. I'm not gonna even check my WhatsApp.
Then you must give me a task, Pela.
No, I'm not going to give you a task. I'll give you. I think now I'm currently preparing you a 4-hour video, and also maybe another 2 4-hour videos, ne, to work on during the long weekend. Then what you're going to do, I can give you maybe some questions to work on.
Okay.
Yeah.
Okay.
Because I wanted us to do electrostatics.
But we did do electrostatics.
Nope, not with me. Oh, electrostatics. Electrochemistry, man. Not electrostatics. Electrochemistry.
Oh, yes.
So this is the concentration, eh? And this should be the time in seconds. Okay.
So it's always a concentration in a rate graph.
Yes.
Okay.
Yes. We start here, we go that side, and then up Nyana Moki, then start increasing again. So
is it each less than 0?
Eh?
Is it still
we're still using delta H less than 0. So this will be my product, which is NH3. Then the reactants, this one will start here, go down, then when it reaches this point, we go up. Then from here, it will go up like this. Okay. Okay, from here it will go up. And then what do we have? Then it starts decreasing again.
Okay.
And this will be my H2. Then the nitrogen will do the same thing, drop, and then reach equilibrium. Then when it reaches this point, it will go up. Everything goes up when the pressure is increased. Né? Then they start dropping, and then the products are the ones that are increasing. Then equilibrium is reached again. So this will be my N2. Né? Let's go through this graph. Let's make sure that you understand the graph. Né?
Okay, sir.
Yeah. At this point here, this is my T1. We already know that this is T1. And then this point here, this will be your T2. Okay?
Okay, sir.
Right. So, at T1, remember the pressure is increased. Yesterday, what did we say about pressure? You still remember what we said? If the pressure is increased, what happened?
Volume decreases.
Eh?
Is it volume? We said that
yes, the pressure is increased. We are increasing what? The pressure. The pressure is increased, right?
Yes, and then the volume. Was it not volume?
Yes, it was volume.
That decreases, right?
Yes. So if the pressure increases, the volume will decrease, right?
And then them will favor the product. It will favor the reactant that produces less molecule gases.
Exactly. Yeah. Exactly. This will favor the reaction that produces less molecule. So this is what we need to focus on. If the pressure is increased, this favors what? This favors the reaction that produces less molecule, okay?
Yes.
Let's go to our graph. Our reactants, we said we have 3 plus that 1 there, which gives us 4, and then this is 2. So this tells us that the reverse reaction, the reverse will give us 4 number of molecules, and the forward reaction gives us what? Gives us 2. Remember, the reactant is 4, this one is 2. So how did we get the 4? 3 plus that 1. So the reaction that, if we increase pressure, the reaction that produce less molecules will be favored. So now tell me which reaction is favored if the pressure is increased?
It's the NH3.
What is the NH3? Remember, we are increasing pressure, and we said that if the pressure is increased, we will favor the reaction that produces less number of molecules.
Yes, and that reaction is the forward reaction.
Exactly, that reaction is the forward. So this tells us that here the forward reaction is favored. And you can also see that from the graph that at T2, after the temperature, after the pressure is increased, the number of the concentration of the products are the one that are increasing. So this tells you that we are using more reactants to create what? More products.
That's, yeah.
You happy with that?
Yeah.
So now we say that at T1 we can see that the rate of at T1 the system reaches equilibrium. So the concentration of the product and the reactants are constant. And then at T2 this is where the pressure is increased. You know? So this guy here, it's where the pressure is increased.
Okay.
So as the pressure is increased, this decreases the volume, right?
Yes.
Right. So the system will favor the forward reaction, which produce what? Fewer number of molecules.
Hello.
I think you'll be able to do the decrease in pressure, but we're gonna start with the decrease in pressure tomorrow, né? Then once we are done with these graphs, we're going to start with the equilibrium constant.
Okay.
Then after the equilibrium constant, we're going to eat past papers. Then we are done with chemical equilibrium. So I think tomorrow, if morning we can do the graph, start with chemical equilibrium, and then on the afternoon we finish chemical equilibrium. So this tells me that during the long weekend you'll be working on past papers, né?
Okay, sir.
Yeah, I just want to use this 5 minutes for my upcoming lesson. I have a lesson. You wanna join?
What lesson is it, sir?
Calculus.
Yeah.
Okay, I'll send you the link now.
Okay.
Is the link not appearing on the system? Because I think you are also added on the improvement program.
I'm not on the improvement program.
Okay, it's fine. So there's no link appearing on your portal.
On my portal. No, there wasn't a link on my portal.
Okay, it's fine. Let me quickly check that.
Okay, then I'll go recheck then.
Yeah, or I can send you the link on Konje, your name is Konje, what's your name?
Emilia.
No, the one on the system, I don't remember. Oh, Bekiwe.
Yes, Becky.
Let's see, you don't have a group. Let me quickly allocate a group net for you. Spark Improvement Program. Yeah, so if you can go to, if you can log in now, net. I'm just gonna update so that you can definitely see today's class, net.
Okay, sir.
You see, there are 48 learners in the program, but on this group. But I know there will be 15 learners. Let me quickly fix this. What's wrong? Okay. I'm just gonna include you on the class.
Okay, sir.
Sharp, sharp. If the link is not appearing, please make sure that you
Text.
yeah, or I'll also send the link now. Ne?
How long is the class, sir?
1 hour.
Okay, that's all.
Sis. What's wrong here? Okay, let me save. And that's it for today. Sharp, sharp, ne?
Okay, so sharp, sir.